Welcome everyone to Learning with Rev. In this video, we are going to be expanding on our series when we are using the Large Fish Dataset. And in our previous video, we went over transfer learning, and in this video, we are going to build our own convolutional neural network from scratch. So, in that previous video, we loaded a pre-trained model, we chopped off its head, or pretty much the bottom of the network, we added our own classification layers, and we trained it, and it was great. In this video, we are going to load our data the same way, but instead of having a pre-trained model, we are going to have an input, build our own convolutional layers, and then we are going to and then we're going to train it and get our results. We can see what those results are like. So, to begin, we have all of our standard imports right here. We set OS to recognize the first GPU, and we set TensorFlow to limit memory growth, so that is excellent. And then here are some things we're going to need. We need the input class, we need the model class to build our model. We are using image data generator to load our data from the file. We are not going to use any of the augmentations in image data generator though. We are going to be using convolutional 2D, dense, dropout, flatten, and max pooling layers. I do have videos that go over both max pooling and convolutional 2D, and I will explain what flatten and dropout do as we're building them. We're going to be using the Atom optimizer, which is the go-to optimizer for almost any neural network or any classification network. And finally, we are going to be using also plot model so we can visualize what the model looks like. So, to gather our data, we are going to use the same code that we did in our previous video. This is the location of that data. Image data generator, we are flowing from directory. Our train path and our valid path. Our image sizes are 590 by 445. And our batch size for training is 30 and validation is 20. Now we are going to build our model. So the first thing we need to do is we need to set input layer equals input using that input class. And we're going to set shape equal to 590 by 445 by 3. So in this case, we do have to declare the spatial dimension of our, or the color dimension, often called the channel of our images. They're 590, 445, and R, G, and B. In many cases, it may be useful to reshape your data and make it all grayscale. This reduces your data size by a factor of 3. Our number of pixels will, in this case, each image will have 590 by 445 times 3. That is 787,000 pixels. But if it's just one dimension, one color dimension, there's only 262,000 pixels for the data, for the network to be using. So in this case, it might be useful to do that in the future. If you want, it might speed up your input layer just a bit. Next, we're going to label each of these layers as X just so it's easy. We're going to set conv2d with 32 nodes, a kernel size of 3 by 3, and activation of ReLU. ReLU is our non-linear activation. If we did a linear version activation, we might as well just be using a support vector machine, or maybe another form of non-deep learning, non-neural network machine learning algorithms. And finally, we are going to close this off and set our input layer into that. We're going to actually create a second convolutional 2D, 32, kernel size equals 2 by 2 now. We're just going to change it up just a little bit. Activation equals ReLU, and we're going to pass in X. Next, we are going to add max pooling. If you had too much max pooling, it will shrink your your image too quickly or your activations. So we are going to max pool 2D with a kernel size equal to 2 by 2 with X. And this is going to be, I'm going to call this our convolutional block. We're going to repeat this again, but instead of input layer here, we're going to say X. So that's good. Next, we're going to set X equals to flatten, and we're going to pass X to it. In this case, it's going to take whatever the size of our data is and flatten it to 1 dimension. And we'll see that when I display the model in architecture here. And we are going to say our output equals a dense layer of 9 with a activation of softmax. So softmax will be how we essentially classify on one of the 9 classes here. And finally, we are going to set our model equal to our model class. In this case, our input is going to be our input layer, and our output is equal to output. So essentially what is going on here is it is going to build a model. It's going to iterate through everything from input layer to outputs, make sure they're all connected, make sure all the dimensions line up, and it will build that model. So now we're going to start running some code, make sure we didn't make any mistakes along the way, which is completely possible. And we did make a mistake here. So kernel size for max pooling. Max pooling is supposed to take pool size, not kernel size. So that's the great thing about using a Python notebook here, is we can just do that, and we are good. So now we're going to do model.summary, and we can see here we have our input layer, convolutional layer, another convolutional layer, decreasing slowly in size from that original. We pool, which is actually going to decrease the size of our image by a factor of 2. Convolutional again, and pool one more time. Then we're going to flatten it. So if you multiply 145 by 109 by 32, you will get this value, 505,760. Then all these activations are going to get fed into 9 final in our final dense layer, and that is what it's going to classify on. And we can do a plot model just so we can see what's going on, and this is what the model looks like. It's all linear, nothing skipping anything, it's just a very linear network. Input, convolutional pooling, convolutional pooling, flatten, and dense. So what we are going to do now is we are going to set model.compile, and we are going to set our loss equal to categorical cross entropy. I always misspell it, so I am just going to paste it in from another location that I have. Optimizer equals atom, and we're going to say 0.01 is our learning rate. And we are going to track metrics of accuracy. This is a list, so you could build your own metrics, and there is a tutorial for that online somewhere. Then we're going to fit our model. Essentially, we're going to say train this model here using train generator, validation data equals valid generator, and we're going to say epochs equals to 7, because I think we should get good results within 7 epochs. So as this is booting up, it is building the network, building the graph on the tensor, on the cores on the GPU here. So that is good. And it's going to take about 1.5 minutes per epoch. Everyone except for the first epoch should be pretty quick. So that is good. And we will pause right here, and I will be back soon. And our training is just finishing up right now. It's just finished our 7th epoch of training, and now we are going through the validation of our last epoch, and we'll see the results here in just a few seconds. As we can see, throughout this entire process, our validation accuracy, which is what we want to focus on here, has been increasing, and around here it decreased, but at the very end it popped back up. And our standard accuracy started significantly lower than our regular accuracy, but it did creep up eventually, but it never surpassed it. I do want to make a note, there's one thing I did change here. I made a mistake. I did not include the dropout layer. I added it between our two convolutional blocks, so before or after our first pooling layer, but before the third convolutional layer. So what dropout does is it drops out a random number of nodes, or not random number, but random nodes at a certain percentage. So in our case, I said drop out 20% of the nodes between this layer and this layer. And every time it trains, it takes a random 20% of those nodes and drops them. This prevents the network from overfitting. So overfitting is when you are memorizing your data instead of learning from it. When you overfit, your accuracy is significantly higher than your validation accuracy. In a perfect world, they would be the same value. But when we add dropout, it hurts the network while it's training. But when it validates, it actually removes that dropout and it uses all those nodes. So that is why our validation accuracy is higher, especially early on, significantly higher. And then later on, the difference does taper off. And we do finish at an accuracy at 99.11. Very good accuracy for the data that we have. And this is how you train your own network. You have your imports, you take your data here. We now build our model, some convolutional blocks. So we have two convolutions and a pooling. You could do a convolutional and a pooling, convolutional pooling. Problem with the pooling is it reduces the data size very, very quick. So you lose some of those small details. Then you don't have to build the summary or plot it, but this was just for showing you. We compile it, setting our loss, our optimizer, and metrics, and then we fit with our fit generator, with our train generator, valid, and number of epochs. So thank you all for watching this episode of Learning with Rev using the Large Fish Dataset, and we build our own network. If you like this video, please give it a thumbs up and share the video. If you have any questions, please leave them in the comment section below. I want to thank you all for watching, and I'll see you next time.